Hi, my name is Scott Whitney, and I'm a student in 549. I'm going to be today doing my oral presentation, and I think I've got a rather interesting topic. The topic is IPsec, which is IP security protocol, and I'm going to discuss some authors' implementation of IPsec. And I'm going to really show how this technology is required to properly deliver a new smart grid for this country. And I'm also going to address a little bit about some new research areas that are required, which kind of bridge the gap between IPsec and and the smart grid. So that was slide one. Let's go to slide two. So the agenda today, in specifics, is I'm going to talk a little bit about IPsec, what it is, and why you should care. I'm going to talk a little bit about the paper implementing IPsec, and just briefly, I'm going to talk about some key characteristics of their implementation, and then what some of the authors' conclusions were, as well as some of my own. And we'll talk a little bit about the smart grid, why we need it. It's certainly a important, necessary, crucial undertaking for this country. In the next 50 years, it is absolutely important that this country modernizes our antiquated electrical distribution system. And we need to do this. One is because I think we all agree that there's a need to rely more on renewable or green generation sources, and we also need to we need our electrical distribution, just the equipment and the technologies that are based on are 100 years old. So we need to bring our distribution network in line with our current knowledge in both information technology and in electrical engineering. Then I'm going to talk a little bit about some of the smart grid ethical and technical considerations. As this is a securities and ethics class, I'm going to talk about some of the ethical implementations of the smart grid, because certainly there are some, and there will be a lot of people in this country that will refuse to allow a smart grid enabled meter at their home. There are people that view it as a violation of their personal privacy. And then also I'll talk about some future uses of IPsec and some conclusions. So slide three. IPsec. Why is it important? Well, because it's used in a lot of places where we need authentication, integrity of the data, and confidentiality of the payload. That's places like virtual private networks, which VPN, which allows us to connect to the university or to our corporate domains without any fear of eavesdropping between your home and the target. Now, of course, that doesn't say that, and we've had this happen at my work. It doesn't say that an eavesdropper, if they've violated the integrity or if they've put malware on your system, if you open a VPN channel to your company and with a PC that is infected, you can still infect your corporate network, because that PC starts to behave just like you carried it into the building. So that's that's an interesting thing. But VPN is cool. It allows people to work from home. It allows people to do business and commerce over the internet. IPsec is used for Windows Vista security features. It's used for as a mandatory feature in compliant implementations of IP version 6. IPsec is part of the future for IP-based communication. Okay, that was slide three. Let's go to slide four. Let's talk a little bit about the paper. I mean, the paper is these authors' implementation of IPsec. They took some IP basically some IPsec protocols and advanced them and molded them to what they thought they needed to be. So what makes it unique? Well, one of them is that it's freeware. I guess before this paper, there was a lot of people that were trying to claim copyright or something like that on IPsec. So the authors were trying to make this freely available in the academic community for more research and for continued interest. And it seems like they were able to do that because, as we know, IPsec is still a very active algorithm that technology on the internet. So what makes it unique? Well, they did a lot of kernel patches. So they they have the ability of the kernel for the for the algorithm to uh, for patching for processing incoming and outgoing IP datagrams, kernel patches for maintaining transformed database and policy table, and then they have some specific um, functionalities that they built into. And these are really details that I don't know if they're that exciting, but certainly they did some new things and they advanced the IPsec a little bit. So what the transform database is used to control what IPsec transforms are applied to outgoing packets. So it includes things like session keys, replay counters, SPI information such as remote IP address and security protocol. It's a hash table in the kernel, and they use this radix tree code because it was already debugged, and they had some functionality built in. Not really that interesting. But what was really exciting about this paper is they did, which really is the whole basis of my talk today, is they did a lot of really cool analysis of what the impact, performance impact of IPsec was going to be for systems. I know that I have a buddy that runs all of his networking stuff through VPN, and there's an impact for that. You have more security, but you're going to have your latency is going to be larger, and you're going to have your data rates are going to be slower. And so the authors decided to take a look at, well, what are some of these impacts? And what they did three evaluations. They did ping, and then they did a 15 megabyte data push with UDP and a 15 megabyte data push with TCP. And what they did was they did some analysis with different levels of encryption. They did a tiered structure. Well, this is no encryption performance with IPsec. This is no encryption without IPsec performance, and then this is performance with minimal complicated complexity security algorithms, and this is performance with a very complex computational intensive algorithm. And what they found was that quite clearly was that the cost of IPsec is related to encryption. It's not. If you can run IPsec without without any encryption, of course you will have no security. But there's no cost. And they also found that encryption, the more complicated your complex your cryptography method, you will decrease your throughput. And then again, they found that with TCP the same thing. All right, so slide 7. What were their encryptions? Encryption, cryptography, cost, latency, and throughput, not IPsec. And better encryption equals higher cost. And then, like I said, the authors hope that the open source nature will continue interest in IPsec. So slide 8. So let's talk a little bit about the fun stuff. We need to do a little bit of background. We all know we all, I think, believe we love electricity. It's certainly part of the modern experience. We like posters, we like TVs. If you look over in Tokyo and in Japan with the tragedy that's happened over there, part of that is living without electricity, and it has a real impact on the quality of life. We need electricity to maintain our living standards throughout the world. And another thing about electricity is we don't want to pay more for it than we need to. I mean, you don't compete with your neighbor for, well, I've got a better electricity than you, George. You don't compete over electricity. It's a commodity. We want the safest, cheapest electricity that we can get. And along with that is that we want a electricity that's footprint that's going to be that can be used in the future. So we all know we're running out of fossil fuels. We all know that there's environmental impact, and we know that in this country we need to continue to rely more and more on green-based or renewable supply. And one of the reasons we can't do more of that is because of the fact that green power is not consistent. It's dark outside right now. I have the lights on, and if you can't rely on the solar power right now for electricity, and the whole backbone of our electrical grid in this country is based on produce it now, use it now. There's no storage of electricity in this country, and that presents a real issue. The other is that we have large distribution centers that are large generation centers to produce electricity. And with green, you might have every home able to produce electricity for certain times of the day to cover their use with renewable energy, and that really distributes your generation and really increases the complexity of merging supply versus demand. And in order to do that, you have to be able to communicate almost instantly with other distribution centers to say, hey, we've got a cloud. I need more power from the windmill. I need more power from another source. And all of that information has to be carried on some sort of network that isn't based on the electrical grid, meaning that we're not going to carry our messages with current techniques over the power lines. We need something, a mature technology like IP, and therefore we need security to carry all of this information. Another interesting point is that we also need reliable power grid. Blackouts have occurred. They're no fun when they happen. And first of all, we need to modernize as well. When the power line falls down behind my house in my pool, I shouldn't have to call the power company. They should know instantly that they've got a fault somewhere in the system. We shouldn't be relying on word of mouth. We shouldn't have to have guys go out and walk power lines in the middle of the night. I mean, our technology in our world is far past what we're relying on for the grid. And a big part of the smart grid is that with all of this new communication that's going to happen, you're going to have every second of the day, your house is going to be transmitting out to the internet saying how much electricity you're using, what your credit cards are, and all of that. You need to keep that information private. Okay, so slide 9. What are the technologies required for the smart grid? I already mentioned a little bit about the electrical storage. In order to allow flexible demand and supply, you need to be able to store electricity. And the problem with that is that right now we have to build for peak demand and then idle all of that capacity, and that's not. We all know that that's not efficient. I mean, you want to run your plant 24 hours a day, and